In this example, we're told we have a piston cylinder assembly containing air modeled as an ideal gas. So let's sketch that out. So here's our piston inside a cylinder. We have air in here. We're going to model the air as an ideal gas. Air is going to be our system. So I'll draw a dashed line for that. And air undergoes a power cycle consisting of 4 processes in series. So process 1 to 2, that's a constant temperature expansion. And the temperature and pressures are given. Process 2-3, that's polytropic expansion with n equals 1.3. When it says polytropic, what that means is the pressure times the volume. I'll just write it as specific volume here. Raised to the n, the volume is raised to the n, is a constant. That's what we mean by a polytropic process. So we're given P3 in that case. And then process 3-4, constant pressure compression, where the specific volume at state 4 is equal to the specific volume at state 1. And then process 4-1 is constant volume heating. So question 1 is sketch the, it's not really a question, but sketch the cycle on a PV diagram and then calculate the work and heat transfer for each process in kilojoules per kilogram. So this is actually work and heat transfer per unit mass. And I put per unit mass because it's kilojoules per kilogram. The units give it away that it's per unit mass. Sometimes we call it that specific work and specific heat transfer. So as far as our energy flow diagram, we'll draw some heat going into the air and some work being done by the air on the surroundings. That'll be PDV work because it's moving a piston face, which would be pressure work. Okay, so let's first of all sketch this on a PV plot. So here is pressure on the vertical axis, specific volume on the horizontal axis. And process 1 to 2, we're told it's a constant temperature expansion from a larger pressure to a lower pressure. So here would be P1, and I'll put P2 here. Let me make that a little bit smaller. So we'll put state 1 right there. Higher pressure to a lower pressure. State 2 will be over here. And I know it's to the right because, first of all, it says it's an expansion. So the specific volume is getting bigger. And then secondly, I know if it's a constant pressure process in an ideal gas, for an ideal gas, PV equals RT, that's from the ideal gas law, right? So if it's constant temperature expansion, then this right-hand side will be a constant. And so it'll look like P is some constant over the volume. So that looks like a hyperbola. So I'm going to just kind of sketch it like that. So on this curve, T1 or let me just write it as T is a constant. So T1 and T2 are the same. Okay, so that's going from 1 to 2, and then from 2 to 3, we're told it's a polytropic expansion with n equals 1.3. As I mentioned before, a polytropic expansion looks like that. So that looks like P is some constant over V to the n. So that also looks something like this. So I'll put that there, and that's also an expansion. So the volume's increasing. And that goes to a smaller pressure, P3. You can see the P3 is 0.3 megapascals. P2 is 0.4. And then from 3 to 4, that's a constant pressure compression from V1 to from V4 to V1. So if V1 and V4 are the same, it means it's right along this line. So this is V1 and V4. And it's constant pressure compression. Compression meaning that the specific volume is getting smaller. Let me just put in the V3 and the V2 here. And we say that P4 is equal to P3 because it's a constant pressure compression. And then process 4 to 1, this is state 4. And then from 4 to 1 is constant volume heating. And that gets us back from state 4 to state 1. Constant specific volume. So this is our cycle going from 1 down to 2, constant temperature, 2 to 3. I'll just say that PV raised to the n is a constant. From 3 to 4 is constant pressure, and 4 to 1 is constant specific volume or constant volume. So that's what our cycle looks like on a PV diagram. For a cycle, we start and end at the same point. Okay, so that's item 1, and now we're asked to calculate the work and heat transfer for each process in kilojoules per kilogram. So to find that work and heat transfer, the work is going to be PDV work. We already talked a bit about that. So to find the work, just in general, it's going to be integral from some start. I'll write it as initial to some final volume, PDV. And since we want it per unit mass, right, we're asked to find it in kilojoules per kilogram, I'll just divide through by the mass. So that gives me the specific work, which we'll write as a little w, like a lowercase w. That's just the work divided by mass. And that'll be the specific volume initial to specific volume final, P times the small specific volume change. Okay, so this is what we're going to use to calculate the PDV work for each process. So let's go ahead and do it for the first process from 1 to 2. There we know the temperature is a constant. And so one thing I guess I should mention, in order to evaluate this, we need to know how the pressure varies with specific volume. So we're dealing with an ideal gas. So I know from 1 to 2, I know we're dealing with an ideal gas that's undergoing a constant temperature process. So this right-hand side of this equation is a constant. So the pressure will just be P is equal to the gas constant for air times the temperature divided by the specific volume. So that's how the pressure varies with the specific volume. So we'll take that expression and substitute it in up here and then evaluate the integral. Okay, so the work, specific work, will be the integral as we go from specific volume 1 to specific volume 2. So this is the from process 1 to 2. Substitute in the pressure. Well, R and T are constant, so I'm going to pull them outside the integral. And then I'm left with dV over V. So that's a natural log. That integral is a natural log. So this will be RT times natural log of V2 over V1. Okay, so that's the specific work in going from state 1 to state 2. Now I have to figure out what all those values are. So first of all, we know that the gas constant for air, you can look that up, but it's 0.287 kilojoules per kilogram Kelvin. That's one worth remembering because we deal with air frequently. Temperature 1, or just the temperature, we can call it. So the temperature here is the same at 1 and 2, right? It's a constant temperature expansion. So let me just write it as temperature. Temperature T is equal to T1 equal to T2, and that's 600 Kelvin. Now we need to find the specific volumes at 1 and 2. Those weren't given, right? We were just given the pressures at 1 and 2, but not the specific volumes. So to find the specific volumes, I can use the ideal gas law. Again, I could just take this expression and rearrange it to give me the specific volume. Right? Because I know the temperature, I know the gas constant for air, and now I'm given the pressures so I can calculate the specific volumes. So if I do that, V1 comes out to be, let's see if I did that calculation. Yeah, it's 0.3444 cubic meters per kilogram. And then V2, specific volume at 2, is 0.4310 cubic meters per kilogram. So again, that comes from the ideal gas law. So when you work it out, you'll get the specific work from 1 to 2. It comes out to be 38.6 kilojoules per kilogram. Okay, so that is just PDV work. Now to find the heat per unit mass for that process, we'll make use of the first law, because the first law involves heat transfer and work, and we already know the work now. So we'll write out the heat the first law. Looks like this. And we're going to write it all per unit mass. So this will be, instead of the change in total energy of the system, it'll be the change in the specific total energy of the system. Instead of the energy due to heat transfer, it'll be the energy per unit mass due to heat transfer. And I'll write that as a little q. Instead of work, we'll just do work per unit mass, and I'll write that as a little w. So we're trying to solve for the q here. We already know the specific work that was just given right up here. As far as the change in total energy of the system, that's going to be change in the specific internal energy plus change in specific kinetic energy plus the change in specific potential energy for the system. But since our piston cylinder arrangement isn't changing velocity, it's a quasi-static process, so the velocity is always close to zero. And we'll assume that even though the center of mass of this, it may be changing the way I've drawn it here, that change in center of mass would be very, very small. So, and the density of air is also pretty small, so the change in potential energy would be negligible. So we're going to just ignore both of those. So those are both zero. If you were working this out, like for a homework problem or an exam or something, I would encourage you to write down why these are zero. Don't just set them equal to zero. I would write down explicitly why they're zero. I'm not writing it down here for the sake of time. I'm actually saying it in the recording, but of course during an exam you don't have a recording of your thought process. You have to write everything down. So you would want to write it down just for clarity and put it on record. Okay, so what this then tells us is the change in the specific internal energy, which is U2 minus U1, is equal to Q into minus W by. So in order to find the Q into, I'm going to have to find the change in the specific internal energies from state 1 to state 2. Now in order to do that, I'm going to make use of the fact that I'm dealing with an ideal gas, and I know for an ideal gas, write it over here, for an ideal gas, the specific internal energy is a function only of temperature. So what I can do is, since I know the temperature at 1 and 2 are since they're the same, that means the specific internal energies at 1 and 2 will be the same as well. So that means U2 is equal to U1. So U2 is equal to U1 since T2 is equal to T1, and U for an ideal gas is just a function of temperature. So that means then that Q into is equal to W by, so that means the Q into is 38.6 kilojoules per kilogram also. Okay? All right, we're making some good progress here. So let's move on now to process 2.3. That's the polytropic expansion with the n here, the exponent on the specific volume equal to 1.3. And we're also given the final pressure there. So we're going to follow the same procedure. We're going to calculate the work by doing PDV work right here. And then we'll use the first law to find the heat transfer. So 2 to 3. The work will be the integral of PDV. So this, we're going from V2 to V3. All right, PDV. But we know that the pressure is related to the specific volume here through this polytropic expansion relation, or this polytropic relation here. So I'll just rewrite the pressure. That'll be equal to a constant divided by little v raised to the n. Now to find that constant, I can find that constant from the state 2, right? If it's a constant during this process, that constant will also be equal to P2 V2 raised to the n, because I can just plug state 2 into there, or I could also plug in state 3 into here, P3 V3 to the n equals a constant. So let me just go ahead, since I know the specific volume at 2, and I know the pressure at 2 that was given, let me just use state 2 to find my constant. So I'm going to do that, and then since it's a constant, I'm going to pull it outside the integral. So I have P2 V2 raised to the n times the integral of V2 to V3 of dV all over V to the n. Okay, well we can do that integral as well. So that'll be P2 V2 raised to the n. This will be 1 minus n, and then we'll have, this will be multiplied by V3 to the 1 minus n minus V2 1 minus n. So this is some calculus here. It's pretty straightforward calculus. Okay, so now we know here we're given that n is equal to 1.3. We know P2, that's given in the problem up here. P2 is 0.4 megapascals. 0.4 megapascals, absolute. V2 we calculated previously as 0.4310 cubic meters per kilogram, so that's given right up here, and we calculated that before. So the only thing we're missing now is V3. Now to find V3, we can, let's just go up here and see what we know. So for V3, we're given the pressure, and the way we can find P3 is we're given the pressure, and we also know it's a polytropic expansion. So let me just write that down here. So we know both of those things. So we know P2 V2 raised to the n is equal to P3 V3 raised to the n. So I can solve this for V3. Right? V3 raised to the n is going to be V2 raised to the n times P2 over P3. So I can go ahead and solve for V3. Right, so I can solve then for V3, and when I do that, I'm going to get V3 comes out to be 0.5378 cubic meters per kilogram, because I'm given all the information I need to have. Okay. Good, and then I can substitute those quantities over into my work expression here and solve for the work, and what I'll get is the work done by the air and going from 2 to 3. This is the work per unit mass. That'll come out to be 36.9 kilojoules per kilogram. All right. Now to find the heat transfer per unit mass, we'll go again back to our first law expression. Let me just rearrange that to solve for Q into will be equal to U3 minus U2. This is Q into from 2 to 3. So it'll be U3 minus U2 plus the work done by the gas from 2 to 3. So all I'm doing here is just rewriting our first law expression. I just rearranged it to solve for the Q into and made use of the fact that I'm going here from 2 to 3. So it looks like that. So the work done by the system we already evaluated. So now we need to find U3 and U2, and for that what I'm going to do is again make use of the fact that I'm dealing with an ideal gas. So the specific internal energy is a function only of temperature. So U2 will be U at T2 equals, what was T2 again? T2 was given to be 600 Kelvin. So we can use an ideal gas table. So I'll put ideal gas table. So from an ideal gas table, we can look up what the specific internal energy is. And that comes out to be 434.8 kilojoules per kilogram. I won't show that process. Hopefully by now you know how to use an ideal gas table to look up like the specific internal energy. Okay, now for U3, that'll be the specific internal energy at the temperature T3. So now that means we have to find T3. We don't actually have the value for T3. It wasn't given. But we can use the ideal gas law to calculate T3. So from the ideal gas law, we know T3 will be P3 V3 all over R. And we know this, the given pressure, I think that was 0.3 megapascals. We know the specific volume, that's right here. We calculated it. R is 287 joules per kilogram Kelvin. So we can calculate T3. And what you'll find is T3 will come out to be, let's see, I've got this written down somewhere, 562.1 Kelvin. 562.1 Kelvin. I'll write it here as well. So we can go back to our ideal gas table for air and would have to interpolate to find the specific internal energy, but we can do that. Just a little tedious, but if you go ahead and do that interpolation, this comes out to be 406.0 kilojoules per kilogram. So now we have everything we need to find the Q into from 2 to 3. And when you do that, that comes out to be 8.10 kilojoules per kilogram. All right, so that's from 2 to 3. Now let's look at the process from 3 to 4. From 3 to 4, that's a constant pressure process. Okay, and that'll make our calculation for the specific work easy, because since it's a constant pressure process, the P can come outside the integral and make that integral very easy. So we're going to follow the same exact procedure from 3 to 4. The specific work is going to be P times the integral of dV as we go from V3 to V4. And again, I can pull that pressure outside the integral because it's a constant in that process. So this will just be pressure times V4 minus V3. Now the pressure, we know, let me just write this down here. P is just the P3 is equal to P4. That was given right up here, right? So P3 is 0.3 megapascals. The other thing, let me just note, is the specific volume at 4 is going to be the same as the specific volume at 1, which we previously calculated here, 0.3444. So let me write down these numbers. So this was 0.3 megapascals absolute. V3 was the 0.5378 cubic meters per kilogram, which we previously calculated. V4, we previously found that was 0.3444 cubic meters per kilogram. Just double check that. Yes. So then we can calculate the work. And so the work done by the air and going from 3 to 4 then ends up becoming a minus 58.0 kilojoules per kilogram. And notice that it's minus, so that means that the work is actually being done on the air rather than being done by the air. Okay, so that makes sense. And the reason that makes sense is because we're compressing the air, right? From 3 to 4, we're decreasing the specific volume. We're going from right to left. So that means that we're compressing the air. We're doing work on the air. So that means that the work done by the air should be negative. Okay, to find the heat transfer from 3 to 4 into the system, I'm just going to again make use of my first law expression, which we had written right up here. And I'll just rearrange it. So this will be U4 minus U3 plus the work done by the air from 3 to 4. So this is again just coming straight from the first law. So here we need to, we already know the specific work. We just calculated that. So now we need to find the specific internal energy at state 4. We know U3, that was just given right up here. We looked that up in a table. We're going to do the same thing for U4. So U4 is going to be the specific internal energy at T4. So we're going to have to calculate that in a moment. And then what we're going to do is we're going to use an ideal gas property table to find what its value is. So to find T4, I can make use of the ideal gas law to find that. The ideal gas law, T4 will be P4 V4 divided by the gas constant. P4 we know that was given. It's the same as P3. V4 is the same as V1. I should make a note of that. V1 and V4 are the same because it's a constant specific volume process from 1 to 4. Gas constant for air we know. So we can then calculate T4. And then if you do that calculation, let's see what T4 comes out to be 360.0 Kelvin. So 360.0 Kelvin. We can then use the ideal gas table, and that comes out to be 257.2 kilojoules per kilogram. And then now we can calculate the heat transfer from 3 to 4. And that comes out to be minus 207 kilojoules per kilogram. Okay, so that's from 3 to 4. All right, almost done. Now we're going process 4 to 1. And I bet you can guess what we're going to do next. We're going to calculate the work from 4 to 1 as PDV work. This one is really easy because we're going from V4 to V1, but they're the same specific volume, so that means it's 0. Right? So the specific work from 3 to 4 is 0. I'm sorry, from 4 to 1 is 0 because V4 and V1 are identical. And then to find the heat transfer, again, we'll use the first law. So that'll look like U1 minus U4 plus the work done by the gas from 4 to 1. Well, we know this is 0. And we have these terms, well, we have most of these already. So we know U4 because we looked it up before right up here. U1, I guess we haven't looked that one up yet, but U1 will be this. We'll use the ideal gas table at T1. T1 was given as, go back up here, 600 Kelvin. It's right up here. So T1 is 600 Kelvin. Again, use the ideal gas property table for that. And if you look up the value for that, it comes out to be 434.8 kilojoules per kilogram. For U1, again, we already know U4, that's given right here. So then you can calculate Q into from 4 to 1, and that number comes out to be 178 kilojoules per kilogram. All right, so we did all the different processes and found the specific work and the specific heat transfer for all of those. Now, one last thing I'm going to do, we're not really required to do this, but let's just evaluate the first law for the cycle. So first law for this whole cycle. So one way we can kind of double check our calculations. So the first law for the cycle, we're going to ignore kinetic and potential energy changes. Here we have, oh, I should do this all per unit mass, so let me change that to delta little u. Let's change that to Q into over the whole cycle minus the work done by over the whole cycle. These are all specific quantities. So this is over the whole cycle from the start to the finish. Well, the change in specific internal energy over the cycle will be 0 because that's a property. Right? Basically, you're saying if you start at point 1, what's the change in the specific internal energy as you start at 1 and then come back at 1. So it would just be U1 minus U1. Right? So this is just going to be 0 for the cycle. So what that means is that the Q into over the whole cycle should match the specific work done by the air over the whole cycle. And so the way we can do this is to find the Q into over the whole cycle. That would be like Q12 plus Q23 plus Q34 plus Q41. That should be equal to the W by, I'm going to drop the by subscript just for convenience. That'll be the same thing, like the specific works for each process added together. Right? We should have those equal to one another. And if you take all those previous numbers that we calculated and work them all out, I think they both come out to be 17.53 kilojoules per kilogram on both sides. So that means we did everything okay, that our calculations make sense, because we know that we should have this, Q into equals W by over the whole cycle, and in fact we do. If these numbers were substantially different, then we'll know that we'll have made a mistake. If they're only a little different, like if this was 17.52 and this was 17.54, then that's probably within numerical error, right? So we've done some rounding, and they're close enough to be considered equal. But if this was 17.5 and this was 6.3, then we'd know that there was a mistake somewhere in the calculations. So it's just a way to double check. Okay, so just to quickly recap, we define the work and heat transfer per unit mass was really just an application of PDV work and making use of the first law, and then using the ideal gas tables to find the various properties along with the ideal gas law. And then it was just repeated application of those things. And then as a double check, we used the first law for the whole cycle, just to double check that everything makes sense, which it does. Okay, we'll end the example there.